Okay, so we're going to start off by understanding how to find the distribution functions of certain things. So let's put the following case. Yes. Let's say we have that the probability of the event of omega is described or denoted as p minus 1p to the power of omega, where omega is in the range of 0 to 1, an open range, and omega is a natural number. Now, we're going to denote a random variable. So RV, random variable, xw, or x omega. That is a piecewise function in this case. So 0 if omega is lower or equal to 2, and 1 if this is greater to 2. So how do we find, simply put, the distribution? In piecewise functions, we have to cover the whole cases. We know that a distribution, whenever we take the probability of omega, so the probability of big omega is equal to 1. So we want to take both cases, right? Whenever this is true and whenever this is true. So this would be something like, right, omega lower than equal to 2 plus this. And this is not equal to 1, simply put. So in this case, we want to find the actual thing. So what do? We start off by saying, okay, we want to find the two cases. So we're going to focus only on this and this. Whenever p x equal to k, right? And we have two cases. So case 1 is whenever we have x equal to 0. And x equal to 0 is whenever we have omega being lower or equal to 2. So this is going to be equal to 0, right? 1 and 2. We know for a fact that this is declared as this, right? So we're going to take this and we're going to put 0 here, plus, same deal, and we'll just add them up like this. But in this case, we're going to add 1 and 2. So 1 and 2 equals. So if we just normalize this, not normalize, but continue calculating, this is going to be p times 1 plus p1 minus p plus p1 minus p squared. So we get minus p plus p1 minus p squared, which can be denoted as 1 plus 1 minus p plus 1 minus p squared. And that is going to be the p of x equals to 0. Now how do we find the other part, which is this little guy? Well, when x is equal to 1. So let's do that. X equals to 1. In this case, is going to be 1 minus its complement case, right? So if we do this, we'll get 1 minus this whole thing, right? Right? That's pretty much it. So if we just calculate this, this will give us the actual thing that we need. That's it. That's pretty much it. This will be also equal, right, to the sum of n omega starts at 3 of p1 minus p omega, because of we start from something greater than 2, so omega has to be equal to 3. We begin at 3, and we just do the summation, and that's it. Remember that when we sum stuff, it can be denoted as an OR case. So it can be like whenever the omega begins at 1 or 2 or 3 or 4, it doesn't matter. So yeah, that's pretty much how you solve this type of exercise. So now, let's go ahead and take an exercise from our actual lecture that is really similar, which is this guy here. Let's just copy it and just paste it here. We know for a fact that we have p of omega is given like that, where p is from 0 to 1, and we are defining this random variable yn omega equals to omega mod modulus of n. So whenever we have yn omega, it's going to be equal to omega mod of n, right? This is going to give us that omega is going to be k plus jn, yes, whenever j is part of the natural numbers, and k is like that, right? So to just to show you an example of how this works, let's just say, I don't know, k plus jn. Let's just take 2 is going to be k. So let me just rewrite this here. K. This is going to be plus, I don't know, let's take 2 for j times n, 3. In this case, n, it is greater than k, so that works out. And this is going to be j. And how much is this? 2 plus 6 is going to be equal to 8, right? So omega is equal to 8. And whenever we do 8 mod of 3, we're dividing 3 divided by 8 is going to be 2 times 3 is 6, and 8 minus 6 is 2, so we get 2, which is equal to k, as you can see. So that's how it works, basically. So we know for a fact that this is going to be our omega, right? So omega is this. What I want to do is whenever they give us a random variable with omega, we want to clear omega. We want to know what omega is, what gives us omega. That's the first step. So first step is find or solve for omega, basically. Solve for omega in our random variable declaration. Once you have found the omega, right, you want to start by, let me just go and scroll this up. Was it up or down? Yeah. We want to start with the usual declaration. We take the random variable equals to k, and find its probability, meaning that we have, in this case, the yn is going to be equal to k, and we want to find the probability of this. Now the probability of this can be easily put because we know it's going to be a sum, because it's going to be in an OR cases where we have j equals, in this case we stated that j has to be this, right? And so we depend on j to find k, or in this case omega. So to find omega, we have to simply do okay. So we start from j equals to 0, and we do this. We do omega is equal to k plus jn. And as you can see, that's where we put our variable this solution for omega. So solve for omega, and then what we do is we place it over here. Yeah. The summation, oops, the summation in this case translates to the fact that we have multiple cases that can be not independent per se, but like they're just different cases. So it can be an or. We can choose j as equal to 0 or j equals to 1, j equals to 2. It's an or case, so we have to sum them up. So we have this, and we know that the probability of omega, right, as already stated here, is this little guy, yeah? So in this case, we're going to do p1 minus p k plus jn, simply put. Now we solve for, well, we're going to solve this basically. So we can take this guy and the term of k out of the way because it doesn't depend on j. So we can put it here, and then 1 minus p k, right? Then 1 minus p jn. Now, we want to see the structure. We have to use the geometric series, in which we know that whenever we have, this is going to be equal basically, right, to 1 minus r, right? So for example, if we have, I don't know, doesn't matter what we have, but let's imagine we have this, and it goes to n, and we have, how was it again, r, right? And this is going to be I, yes? This is going to be equal to 1 minus r, right? So in this case, if we present the same formula in our situation, we use this formula in situation, copy this as well, we can see that in this case, r is going to be equal to 1 minus p n, yes? And this is to the power of j, right? So we can do 1 minus p to the power of n. That's going to be equal. So we can do the following times 1 minus p n, which in turns gives us this little guy here. Just erase this 1 here. And we just put it like that. And that is our solution. That is simply the end solution for this exercise. That's how you find the distribution, so to speak. So again, the first step is solve for omega in the random variable declaration. Then you want to just do the random variable equals to k, right? The random variable, so that's what we did here. And we find its probability. Because it's going to be a lot of different cases with an or, so it's going to be a bunch of pluses. And then we're going to take simply, we're going to place this solve for omega here, where omega is equal to this. And then we just solve, and we get our distribution. That is it. That is as easy as it gets. So yeah, that's how you solve this type of exercises. In this case, where we did, where am I? What is this? Is this study or is this, oh yeah, it's a study. Dang it, I forgot. In our case, what we did here, right, was we first found what omega is, because omega is going to be simply just defined by this. This is just another type of cases. So what we do is, first of all, we take the first case where it's 0, and we find all whenever we get that. So that's pretty much it. So we took whenever x equals to 0 means that omega is equal to 0, omega is equal to 1, and equals to 2. So in this case, we also found what omega is. And then we just placed in the the probability function for omega, where it's 0 and 1, and we go on and on. And over here we use a rule of how you call it, is a complement, so we can find the other distribution. And that's pretty much it.